Chapter 8 is called Solutions and Aqueous Reactions. We have seen a bunch of reactions already, and we talked about reactivity, right? We've seen a piece of sodium being thrown into water, and we can set up that reaction. We can write the little symbol Na, and we know its phase label, that's solid. And then we know that the other reactant is water, and we'll put a little phase label, liquid. And then we know we've seen that hydrogen gas is produced and sodium hydroxide, which is aqueous, right? And so we are producing an aqueous solution here, right? But and we can balance these reactions, and then we can calculate, we can weigh the little piece of sodium, measure it in grams, calculate how many grams, right? That's stoichiometry, gram to gram stoichiometry. Calculate how many grams of water will react with X amounts of grams of sodium, and we can predict how much hydrogen gas is produced, how many moles of hydrogen gas will be produced by this reaction. But we haven't really discussed for all of these other reactions that we've balanced how we would do that and how we would prepare aqueous solutions, how we would make sure that in a solution where solute particles are dissolved and they are there in minor quantities, how would we measure it in solutions? And most reactions are done in solution, and that makes sense that it's done in solution, because if you look at sodium chloride, for example, or any soluble ionic solid, it is tied up. All of its ions or its components are tied up in a crystal lattice, and they're rigid, non-mobile. We already know that sodium chloride ionic solids are non-conductive, right? So that means that these ions are non-flowing, and so it's less likely for them to react with another solid, and therefore we dissolve them, if we can, into solvent. And we don't always use a polar solvent, but most of the time water can be used. Most things are either soluble. That's not true, not most things, but things, ionic chemicals and some polar covalent compounds can be dissolved in water. All right, it's all about polarity and solubility, which we will look at as well. And so then we have free-flowing ions, and they're more likely to react with other ions that might be present, right? And so all of these solutions are homogeneous mixtures, right? Otherwise they wouldn't be a solution, which simply means that we can no longer see the individual components here, right? We can see the solid particles here, but when they are in water, we can't tell them apart. We know it's a mixture of water and sodium chloride, but we don't see the salt, right? It's dissolved and free, and it also conducts electricity now, right? And that's another thing that we're going to look at, right? What when dissolved will conduct electricity and what will not. And so just simple definitions here. We have in a solution, we have two components. We have solute components, the stuff that's there in the minor quantity. In this case, that would be the sodium chloride. And then we have the solvent, which is there in a larger quantity. It is the stuff dissolving. And that's here, that's the water. So that would be the solvent. But it doesn't have to be. But if it's water, it is aqueous. It's an aqueous solution here, right? That's what that means. We can have solutions in isopropyl alcohol, which is another solvent, or we can have solution in oil, or other gasoline can be a solvent. But this chapter focuses on aqueous solutions and calculations with them. Okay, so let's talk about electricity, right? So we do know that if sodium is dissolved in water, sodium chloride is dissolved in water, we can conduct electricity. And it is considered a strong electrolyte. And the person that is associated with the definition of that, his name is Svante Arrhenius. And so you may have heard of Arrhenius acids and bases. And it's based on the same principle. He called things that dissolve and break apart into their components, he called them, and that conduct electricity, he called them electrolytes, right? And then we still do that. And Arrhenius acid is something that breaks apart into hydrogen ions, for example. So that makes it an Arrhenius acid. An Arrhenius base is something that breaks apart an ionic solid, or a solid that breaks apart and produces hydroxide ions. And so those substances that are soluble and produce ions are electrolytes, and those substances that are soluble in water but don't produce ions, that are non-conducting, are non-electrolytes, but they still dissolve, so they must be polar. Okay, sugar is an example of that. And then we have weak electrolytes. Those are solids that are sparingly, or solutes that are sparingly soluble or just slightly soluble, and they produce just a few, or they are really soluble, but they only produce a few ions, and those are weak electrolytes. Looking a little bit closer into how water does that, we should know this already. We know it's polar covalent, and we understand that there's hydrogen bonding between the individual water molecules. It holds them together, these little poles, right, so to speak, and we have this network of water molecules that are held together. And so what happens is, if there's a cation or an anion, it can be, this picture isn't done very well, but it can be surrounded by and so this one isn't oriented properly, and then that one would connect maybe to the see, the white is the hydrogen and the red is the oxygen. And so if you have a cation here, uh, this so-called hydronium ion, and we'll look into how that works in chapter 14 or 15, so don't worry about that right now. But you can replace the central hydronium ion with a sodium ion and whatnot. But look, this explains it a little bit better, right? So here we have these little water molecules, and we're putting solid sodium chloride in the center here. These purple and green spheres are representing the sodium chloride, right? The green one is chlorine or chloride, and the purple one is sodium. And you can see the water molecules ripping here, right, with its positive end ripping these anions off the solid and dissolving it, right? So this is the process of dissolution, and so that happens to soluble ionic compounds, right? So and then here you see the one of the water molecules approaching a cation with its negative oxygen, its polar end, and so it can do that here, right? So and then these water molecules surround the cations and anions, and whether they're, and depending on, here with the white hydrogen to the negative, and so I think you quite get that, how that works, right? And so this produces free-flowing ions, and so you can conduct electricity. In fact, so here are three examples. Here's a sodium chloride solution, right? So you have here in sodium chloride, you put 2 electrodes in there, you hook up a battery or stick it in an outlet, and that light bulb lights up, right? That shows you that electrons are flowing through. That's a strong electrolyte, right? A soluble ionic compound is always a strong electrolyte, okay? And then we have an example here of a weak electrolyte, and we're going to look into that here in a second. This is acetic acid or vinegar. And if you look at the structure and you only have the knowledge of what I've taught you so far, you would argue, well, that should not produce ions. And you would be right based on what I've taught you so far. This is not an ionic solid. It's a covalent bond. It's a polar covalent compound, and it should only dissolve in water but not furnish electrons. Turns out it does a little bit, and I'll show you how that works on the next slide. And then this makes more sense, right? If you looked at the structure of sugar, and I also have that on the next page, this is a non-electrolyte, but it's highly soluble in water because it has a whole bunch of polar OH group, just like water. Okay, in fact, let's just go look at that. Well, it's clear that, right? So the light bulb doesn't light up here at all. You have a solid that looks just like sodium chloride. It's a white solid, right? Sugar. It dissolves, but it does not conduct electricity. You will not see this light bulb. And so you could take any kind of solid if it dissolves, and then you can test it. And you can tell, oh, this must be an ionic solid, or this must be a polar covalent compound. And okay, so let's take a closer look here. Sucrose is the table sugar. Table sugar, you might know from biology if you've had any, is a disaccharide. It has two little sugars bound together with a glycosidic link, but that's completely beside the point here, right? So let's say you don't know any biology. You look at this compound, these, what I didn't draw and what we don't draw in the line structure are the carbons here, right? So we just leave them out. So there's a whole bunch of carbons here. So we have carbon-carbon bonds, which are nonpolar, and then we have a few oxygen-hydrogen bonds. And those are polar, very polar. Not just a few, look how many we have here. We have a whole bunch of H groups. This makes this substance covalent because we don't have any cations and anions bound together, just nonmetals, right? That's a covalent compound. But we have, it's highly polar, and so it is super soluble actually. You can actually dissolve 100 milliliters of water will weigh about 100 grams. You can actually take twice that much sugar and dissolve it in there, right? You can take more than twice as much. You can take like 250 grams of sugar and dissolve it in 100 grams of water. So you really almost have the sugar as the solute. But the solute in this case is sucrose because it dissolves. It is surrounded by the water molecules, and which rips it apart. It needs the water. It's not the sugar that's doing it. But that's beside the point once more. And you may think, well, that's not true. That can't be true, right? But it is. Think about maple syrup or any kind of syrup that's essentially just liquid sugar, right, with a little bit of water in it. So, and over here you have acetic acid, and acetic acid is also polar. But what makes that a weak electrolyte, and you do understand this bond here is polarized, right? So this electron cloud is pulled towards it. So this bond is already weakened a little bit, right? So remember the difference between covalent, polar covalent, and ionic. It's just a difference in electronegativity, right? So if I increase the electronegativity of this oxygen, which I cannot, just by, zapping it or something. But let's say if it was a different atom that had a higher electronegativity, that bond would break and we would have an ionic compound. Well, this second oxygen that's connected right close to it here, right? So this is also a polar bond, right? And so what you really have is you have electron density pulled away from this bond, just enough so that a little bit of this comes apart. So what we have, and I'm going to draw it like this, CH3CO2, which represents this, minus and H plus. So just a little bit of this happens, but it's less than 5%. So most of it stays, so there's this equilibrium here between acetate and hydrogen ions. So that, hey, you go. I mean, that's what I was just telling you about Arrhenius. He said if H plus comes off, we have an acid. And what do you know? We call this acidic acid. And it's exactly because we have and it's a weak acid and a weak electrolyte because just a little bit of H plus comes off, right? And so this weakens that bond. Let me try this one more time. I'm going to draw this out here. So what we have is we have this electron density, this second oxygen here pulling electron density away from this bond. And so just a little bit of it breaks, less than 5%. And so 95% of it is still covalent and together and is hanging on to that hydrogen. And so that makes it a weak electrolyte. In fact, there are a ton citric acid, lactic acid. There's a ton of organic acids out there, and they all have the same structure. They have this combination of atoms. They have this carbon, double bond oxygen, OH. They have this group, and then they have attached to this carbon. So that's that acid part. It's called a carboxylic acid. Right? And then they have some sort of organic group here, whether it's a CH3 group or it could be something cyclic like a benzene. Oh, that's a beautiful benzene ring here, right? Anyway, it just R here, just some sort of organic group. And so every time you have this particular group, you have a weak electrolyte, you have a weak acid, always some of this is going to come off, right? Because this organic junk that's attached, it doesn't matter really what it is. What matters is this combination of atoms makes it a weak electrolyte. All right, so moving on, right? So anything that is soluble in water, any ionic compound that is soluble in water, and I keep emphasizing that is soluble, you'd expect all of them to be soluble, right? I mean, you have cations and anions, why wouldn't it be? But it turns out they are, for various reasons that you'll learn in chapter 14. Some ionic solids like silver chloride is not soluble in water. And so we're going to look at these solubility rules and predict reactions based on them. But potassium bromide is soluble. And so potassium bromide as a solid, when dissolved in water, it'll break. And so that's what's missing here in a way, is that we are dissolving this in water. So that kind of, it's implied by the way this is written that there's water here, because this AQ tells me there's water here, right? So this is a dissolving potassium bromide, and then you have free-flowing potassium and bromide ions, so you can conduct electricity. Same with sodium sulfate. Sodium sulfate is soluble, and it's also important to note that, and remember that, potassium is +1 and bromine is -1. So it's important to remember that these are in a 1-to-1 ratio. And here are the polyatomic ions, and you really ought to know what they are and what their charges are. At least there's like 10 or so that I said that you should know even beyond this class. Now sulfate is -2, and so it requires 2 sodium ions, right? It's important. And so then it doesn't break into Na2+, it breaks into 2Na, right? We have 2 sodium ions, right? So we have 2 sodium ions here and 1 sulfate ion, right? And so we have really for 1 mole, and this is important to note at any moment because this is a concept that people struggle with, right? So if I had 1 mole of this and 1 mole of that, this would actually would have a higher conductivity. And that's because more ions are produced, right? 1 mole of potassium bromide produces 2 moles of ions. But 1 mole of sodium sulfate produces 3 moles of ions. And one of them has a -2 charge, so a higher charge. So that leads straight to a higher conductivity. Looking at weak electrolytes now, acetic acid or any kind of weak acid, how you would know by writing the equilibrium errors here, right? So here we have acetic acid, and it's drawn in a way where we have acetate and then that H plus separated, and so that turns into H plus and acetate ions. But there's an equilibrium here, so there's a little bit of everything here, right? So it turns out that 95% of it is still on, so this equilibrium is very much so on the left, and that's why this is a weak electrolyte, right? Because just very little of it is broken into ions, but some of it is. And since one of these ions is an H plus, that also makes it an acid. This is ammonia here. Now ammonia is a gas. This is so, yeah, it says AQ here, but let's just say this was a gas, and you bubble it into water, and what would happen is it would react with that water to form ammonium hydroxide, which is aqueous, right? So nitrogen, and this is a base, right? Remember what I said about Arrhenius bases? They produce hydroxide ions, right? And so similarly to this combination of carbon double bond O to OH with an R group that made it acid, it is the nitrogen that makes it basic. Okay, so you could have a nitrogen with 3 groups, and it doesn't have to be hydrogen, that will always react with water, and it'll react with, it'll attach to that proton here and rip that off to form the hydroxide, but it doesn't do that. That's to a large extent. Again, we have like 95%, and that's an approximation. 95% or more stays together as ammonia, as the base. Nitrogen bases. Remember, I don't know if you remember that, but you should know ammonia is a household cleaner, and it's basic, and it's because it's an organic base or a nitrogen base, a weak base, and so that forms ammonium and hydroxide, and it's the hydroxide that gives it that base strength. So this is just a summary here, right? Strong electrolytes, weak electrolytes, and non-electrolytes. Non-electrolytes are all the organic polar covalent compounds that don't produce ions like sugar, ethanol, nail polish remover, any kind of organic liquid that has some sort of polarity will produce ionic, non-polar compounds. Okay, so this is just, I've barely just scratched the surface. I'm going to take a break, and when we come back, we're going to look into solubility rules and do some write some equations, predict some reactions.